Let me try to say something. Hello. Hey. Hi. Okay. Welcome to MathSoc's Math2501/2601 revision seminar for 2024. Okay, this is the first part of the seminar. Next part is later today. This first part will be presented by me, Marcin Knežević, and Oscar. Okay, so let's jump into it. Yep, that was just a list of topics that we'll be covering. First part is group theory. Okay, so just to start with some definitions of what a group is. So a group is a non-empty set with an operation defined on it, and this operation is really a binary operation. So that means it takes two inputs inside the set, and it has to output something that's in the set. So that's actually the first axiom on this binary operation, namely closure. So for all A, B, and G, then if we apply the operation to two elements, it should remain in G. And I'm going to refer to this operation as like star or times or multiplication, but it can be really anything. It can end up being addition. And when we perform the operation, we kind of write it in the middle of the two things that we're calling it on. It's two arguments. Okay, so the first thing is closure. Next thing is associativity. So the placement of brackets around the operation doesn't really matter. And that's why we'll typically just not worry about the brackets anyway, and we'll write something like this is like A star B star C. Just because the placement of the brackets don't really matter. And then sometimes we'll even go a bit further and just ignore the star altogether and just write A, B, C. Okay, existence of identity. So there needs to be some element. In this course, we usually call it E. Sometimes this is called 1. But there has to exist some element such that the application of this element to any other element, either on the left or right, doesn't affect that element for any element in our group. Okay, existence of inverses. For all A and G, there exists another element in G. We usually write it using this syntax, such that if you apply those two elements together, you get the identity, and it should be for either order. Okay, and then there's another thing called an abelian group. So if you have commutativity of the operation for all elements, then we call that an abelian group. But usually for normal groups, we can't say AB equals BA. Only for abelian groups can we say that. Okay, we typically denote a group using this tuple. So the set, comma, the operation. Okay. So here's an example. So we have this set defined like so, the set of 2D matrices. Let's try prove it's a group under matrix addition. Okay, so if we just check our axioms, the first thing we can look for is closure under addition. In reality, we know that there are some well-known groups. So the reals under addition is a well-known group. Set of n by m matrices over some field. So in this case, it can be R is a known group. So yeah, let's just see if this is closed under addition, because we have the other group properties from this matrix group. Yeah, we'll have to prove closure and inverses, and also show identities in here. Okay, actually I'll start with identity. So 0, 0, 0 is in S. That's because it follows this 0 plus 0 equals 0 plus 0. Okay, so there's our identity. Now we'll look at closure under addition. So suppose A1, B1, C1, D1, and A2, B2, C2, D2 are both in S. Okay, we wish to show that their sum is also in S. So their sum, I'm just going to call this A1 and A2. So the sum is going to be A1 plus A2, B1 plus B2, okay, and we need to show that they satisfy this. Okay, so A1 plus A2 plus B1 plus B2 equals, after rearranging, A1 plus B1 plus A2 plus B2. Gonna put brackets around these. And then we can use the fact that A1 and A2 are both in S to say that this first thing here is C1 plus D1. And the second thing is C2 plus D2. Okay, and then after rearranging once more, that gives C1 plus C2 plus D1 plus D2, which implies that A1 plus A2 is an S. Well, the associativity of addition for matrices should be clear. So there's that. Oh, and obviously if you plus the zero matrix to any other one on the left or the right, it preserves that matrix. So we have identity there, and we'll just look at, oh yeah, we'll look at inverses. So the inverse for matrix addition is just like the negative of the matrix. So we want to say that if A1 is in S, let's just show that negative A1 is also in S. Because A1 minus A1 will clearly equal a zero matrix. Okay, so if A1 has the same coordinates as this A1 as before, then negative A1 is going to have negative A, negative B, negative C, negative D. And negative A minus B equals, after we factor out the negative A minus B, and then we can use the fact that A1 is already in S. You can apply this. So negative C minus D, and that just equals negative C minus D. So that should give that negative A1 is an S, and we have closure under inverses. So we've shown that S is a group. Okay. We'll go through a bit of a slightly faster way to show that something is a group. We'll typically show that things are like a subgroup of an already well-known group, and yeah, I mean, we'll get to that. Okay, so from the base definitions of groups, can prove some like basic properties that we like usually just take for granted, but these have to be actually proved from the axioms of groups. Okay, uniqueness of identity and inverses. I'll go through uniqueness of identity. So suppose you have an E and I that both satisfy the requirements for an identity. Then what we can say is that E equals equals I dot I. The reason why we can, oh, I should have I dot E maybe. Yeah, E equals I dot E equals I, really. So the first step here uses the fact that uses the fact that I is identity. So doing I dot anything is this just that thing. And then the second equality uses the fact that E is the identity, so applying it to anything doesn't affect it. So that's why we get that if you have any two elements that satisfy identity, they have to be the same thing. Okay, for the next one, the inverse of an inverse is just the thing you started with for any element. This should be pretty clear just because from the properties that inverse has to satisfy, which is AB equals E and BA equals E. So if you have these two properties, that's just by definition like A and B are inverses of each other. So if you look at what the inverse of A has to satisfy, then like because these two equalities, it doesn't matter like the order of A and B, so it's like they end up being each other's inverses. Because for B to be A's inverse is the same things it has to satisfy for A to be B's inverse. Okay, for the next thing, we can just check that it satisfies this inverse property. So I can go, because we know AB inverse is going to be E, right? So we have to show that this thing satisfies this defining property. And we have to do that on the left as well, because there are these two things, but I'll only do one direction. So AB, E inverse, A inverse. Remember, we don't care about the brackets for groups because of associativity. So we can just use B and B inverse and make that the identity. Then we can kind of ignore the identity because the application of it to anything leaves it alone. So we just have A inverse, and that's just our identity. So that's why this third thing holds. Okay, then we have a cancellation law. And this should be clear just by applying A inverse to both sides. Okay, so fields. Fields is like a group with a little bit extra. Specifically an abelian group with a bit more. Okay, so field is a set with two binary operations defined in it. We usually call this plus, well, addition and multiplication. So under plus, F has to be an abelian group. So the things need to commute under addition. And if you exclude 0, 0 is what we usually call the additive identity. So it's the identity for when F is an abelian group under addition. So if we exclude that from F, we should get another abelian group under the other operation. Okay, and then we need the distributive laws. So multiplication distributes over addition always, to the left and to the right. Common examples of fields, the field of rationals, because everything has a multiplicative and additive inverse. The reals as well, complex numbers. With the rationals, it's like you can add and times and invert elements and you still get a rational. So that's why it has the closure for these operations that we're used to. Yeah, here addition and multiplication are the ones that where we'd be used to. Okay, so subgroups. Here's an easier way to prove things are groups. You just show it's a subgroup of another one. So a subgroup is a set that is a subset of a group, and if it is a group in its own right under the same operation as the original group, then we call it a subgroup. So basically, we need A to be non-empty, so it can't be a group. We need closure under this operation, and we need closure under inverse, because identity will get for free if we have closure under the operation and closure under inverse, because and non-emptiness. So if you have some element in there, let's call it like A, which we get from it being non-empty, then we can use closure and existence of inverse to say that, well, not only does A inverse of exist, but if we multiply it with A, the result is still in big A. So this will give us that the identity is there. Associativity should follow from does follow from associativity of the original operation. Yes. Oh, and they have the same identity, which should be clear. Okay, and we use this notation to say that A is a subgroup of G. Yeah. Okay. Example of a subgroup. So let G be a group for any element of G. In G, we define this set. Note that this set relies on G. So this set is any element A in G that commutes with G. Okay, prove that we have a subgroup. So for non-emptiness, it's just the easiest thing would be to show that the identity is in here. We can also show that G itself is in here. So you can say, well, GG obviously equals GG, so non-emptiness. But we can also say EG equals GE, so has the identity. Again, this both gives us non-emptiness. Yeah. So here we have non-emptiness. The next thing that we'll check is closure. So based on just like the expression you need to satisfy if we want an element to be in this group. Yeah, we can say, okay, suppose x and y and CG, they have to satisfy these two things. Proving closure, we just need to show this thing, that it implies this. In other words, that. And this should be clear because g x y equals x g y. So here I've applied this thing, and then applying the next property, which we get from y being in CG, we'll have x, y, g here, and that's exactly what we need to show. Note that I kind of ignored the brackets. Again, that's just because of associativity of the group operation, but here it is a bit more explicit. So yeah, here's using the fact that x is in CG, and here's using that y is in CG on this line. Okay, so I have closure. Okay, on to inverses. Okay, so if you have an x in CG, you want its inverse to also be in there. So you need to show this. Okay. And we kind of want to use this fact. So I'll say G x inverse. Okay, I'll get an x inverse next to this. Sorry, I'll get a g inverse next to this x inverse, because then I can factor the inverse out and then apply this. So g x inverse equals gx inverse, and if I apply g inverse and g, I haven't actually changed anything because g inverse g is just the identity. And then here in the middle, I can factor this. I can take the inverse out from the law that we introduced earlier. So gx inverse g. Note that x and g now swap when we take the inverse out. Okay, and then now we can apply this fact. So g xg inverse, because x and g commute. Okay, and then we now undo taking the inverse out. So we expand g inverse, x inverse g, and the g inverse at the start vanish and become the identity. Okay, so we have shown what we want. But yeah, same thing here. Okay, so by the subgroup lemma, since we've shown that CG is non-empty and that is closed under the operation, and inverse for all elements, it is always going to be a subgroup of G. Okay, so subfields. Let E be a subset of the field F. Then we have a subfield if we have these things satisfied. So existence of a non-zero element. We have closure under addition, additive inverses, closure under multiplication, and closure under multiplicative inverses. The reason why you need a non-zero element is because if you have just the zero element, then just this excluding zero, we need this to be a group under multiplication, but this is clearly just going to end up being non-empty. So yeah, similar thing to the subgroup lemma, it's just you have kind of like two things that need to be a group. Okay, and we use the same notation. Okay, So we can have a mapping between two sets, just like you might have a function between two sets. Okay, we call the mapping a homomorphism if it maps from a set G to, a group G to a group H. We call it a homomorphism if it satisfies this for anything in its domain. So basically, the function sort of like can apply it over the group operation, and it becomes the codomain's groups operation. Okay, and if this is a bijection, then we call it an isomorphism, and we say that G and H are isomorphic, which in group theory terms just means that they function as virtually the same group under at least the group operation. They work in the same way. And so group isomorphism, being isomorphic, ends up being an equivalence relation for groups. Should make sense because this is a bijection. Okay, properties of homomorphisms. We can show some of these things. So inverse maps to inverse. So f of A inverse equals f of A inverse. And we can show this by just showing the inverse axiom. So f of A, we want to show that this left thing is the inverse of f of A. So f of A, f A inverse equals, and now we can use the fact that f is a homomorphism. This equals f of A inverse, which equals f of E, which equals, now we just need to show that this thing holds. Okay, well, suppose it does, then yeah, we get this. So inverse maps identity should give us this other thing. Yes. Okay, we can show that the identity maps to identity like so. So f of E equals f of E dot E. You can do that with the identity. Equals f E. And then just by applying the inverse of this to both sides, we will get that this implies that FE equals E prime. And then we can use this fact to reason this step for inverses mapped to inverse. Okay, so here's a fun isomorphism proof. So show that the reals under addition is isomorphic to the positive reals under multiplication. So the reals under addition, in this case the identity element is 0, by the way, and for reals under multiplication the identity element is 1, but we can further restrict that group to just the positive reals as well, because the multiplication of two positive numbers is just positive, and the inverse is the multiplicative inverse of a positive number is still positive. So okay, basically we're looking for a function, right, that by the nature of the meaning of homomorphism satisfies the following thing for all real numbers: f a plus b equals f of a times f of b. So we need a function that satisfies this property. If you have a bit of a think about it, about maybe well-known functions that you know, and think what satisfies this, you might end up realizing that, oh, we can just have the exponential function and since the exponential function is defined for all real numbers, we immediately get that the exponential is a homomorphism. So now to show isomorphism, we just need to show that this exponential function of ours is hopefully injective and surjective. Okay, for injectivity, suppose xa equals xb. We need to show that this implies that a equals b. And it's really simple, just apply ln to both sides. So that's how we get injectivity. For surjectivity, we need to show that for anything in the codomain, there exists something in the domain that gets mapped to it. So consider A in the positive reals, i.e. A greater than 0. We can take ln A, so which is an element of the reals. And if we do, we can just see that x of ln A equals A. And note that ln A is always going to be defined when A is greater than 0. So we can always take ln A without worrying. So that gives us surjectivity, and this is injectivity. So we have that it's bijection. So there's our proof. Okay, kernel and image. Consider a homomorphism. We define two special types of sets that come from this mapping. The kernel and the image. So, okay, kernel of f is this set. It's anything in the domain that gets mapped to the identity in the codomain. And we have the image of f is this set. It's anything in the codomain that gets mapped to by something in the domain from f. Okay, here's an example. So suppose we have a group with identity element, okay, and then another group H with identity element F. Okay, and we have some homomorphism phi. Okay, show that if G is in G and K is in the kernel of phi, then this is also in the kernel. Okay, so this is just like what we have to show just by definition of the kernel. Note that again, F is the identity in H. Okay, suppose these two things hold. Let's go about showing this, and we can do that by applying the homomorphism. So if we start from this, we can apply this to make it like so. Note that I can skip straight to here because it's just like applying it's just using the homomorphism fact twice for each of these multiplications that we started with. Okay, so this equals, let's use the fact that k is in the kernel to say that this is f. And we had a property that we proved earlier that this is just phi g inverses. So inverses are preserved. So this just equals phi g inverse, which is just the identity f. So we've now shown this. Yep, so that's exactly what I was saying. Oh, that does this for groups. Groups is done. Okay, I'll move on to the next one. So after groups we have vector spaces. Might just chill for a second and then we'll hop into it. Okay, vector space is time. So, V is a vector space over a field F if we have the following things. So, V under addition is an abelian group, can scale and multiply by elements of the field so you can multiply with the field element with an element of the vector space, and it has to satisfy these things. Okay, and then we can talk about like alpha V for different alphas. So because F is a field, it will contain 1 and 0 and other stuff. We need this to be satisfied, and these two properties. So scalar multiplication needs to be able to be applied over the first addition for the two vectors, and the scalar multiplication also needs to go over scalar addition. Okay. Subspace theorem. Suppose we have a non-empty subset of the vector space, has to be non-empty, then it can be a subspace if we have this holding for any element of the field and any two things in U. So this will give us closure under addition. It'll give us closure under scalar multiplication as well, and it ends up giving everything we need. We'll see that in a sec. So why does this suffice? Okay, so for the existence of the vector 0, we can just lambda equals -1, which is always going to be in our field, and then take any y and x that are equal in U. And we know that U has to contain something because it's non-empty. Because then we'll get what, -1x plus x, and then 1x is just x. So what I'm implicitly doing is changing these brackets to be here. -x plus x equals 0. Okay, closure under scalar multiplication. That works by just setting y to 0. So we have x in U implies lambda x in U. Closure under vector addition, just said lambda equals 1 and you have x plus y. Okay, existence of vector inverse, set y to 0, which we now know U must contain, and set lambda to 1. So x in U implies -x. is in U. And that's all we need for subspaces. So let X be a non-empty set and Y be a subset of X. So prove that this is a subspace of fx, which is functions that map from x to the reals. Okay, so this U is any function that is 0 for any y in Y. So, so for non-emptiness, we'll just show it contains the 0 function. So the 0 function is the one that maps x to 0 for any x in x. And because y is a subset of x, it's also going to map any y in Y to 0. Okay. So now we get that U is non-empty. Okay. So for that closure thing, suppose that f and g is in U. Okay. So that means this. Then lambda f plus g of y for any y in Y is just this. So lambda f of y plus gy. So I'm just using this property of how like real functions work, because the reals are filled. Okay, equals lambda times 0 plus 0, because we have this, so that just equals 0. And that's all we need. Yeah, so by the subspace theorem, we have that U is a subspace of functions from x to the reals. Okay, span. Suppose we have a finite set of vectors that is a subset of our vector space. We define the span of S as all the possible linear combinations of elements in S. So anything that looks like this, where, and by linear combinations we mean we can sum things up and scale them at the same time. Scale them by something in the field. Okay. So it's quite easy to see that span S is a subspace of V because it's just closed under all linear combinations. By definition, a span is the set of all linear combinations of elements that it's of S. Okay, and in the case that span S equals V, we say that S spans V, or that it's a spanning set for V. Linear independence and dependence. So we call a set, a finite set, linearly independent if and only if this being true for some values of lambda I must imply that lambda I equals 0 always. And we call the set linearly dependent otherwise. So basically, there's no linear combinations of elements that end up being 0 besides the trivial linear combination of just all the lambda i's being 0. So what that means is that you can't write the vectors as a combination of each other, because if you were able to, then you could make one negative and have the other linear combination in there and get like non-zero values for some lambda i's that ends up making this equation true. Okay. So linear independence means that, we can't express any of the vectors as a linear combination of the other vectors for the reasons I just explained. Okay, so we have this set of vectors, which are just functions defined like so from the reals to the reals. And we're asked to prove that B is a linear independent set. So first we consider this equation And just, yeah, by definition of linear dependence, we just got to show that the alpha I values are always, not always, but the alpha I values just have to be 0. Okay, so in other words, we have to show that this is 0 for all x. Okay, and so, okay, the reason why we get that as we consider the limit as x approaches infinity, to imply that alpha 0 equals 0, is because if we take the limit as x approaches infinity, okay, so this thing just ends up being e to the negative infinity, which is just 0. Same with this and same with this. So basically everything else like just vanishes because yeah, we can put the limit inside of here because exponentials are continuous. Okay, so we get that alpha 0 must be equal to 0 for this to hold. Okay, then if we multiply both sides by e to the 2x, we get this. That's because we can just disregard this alpha 0 here. And now if we honestly just do the same thing by considering limits as x approaches infinity of both sides, the right-hand side is obviously going to be 0. The left-hand side, this limit applies. Hang on, I should be considering the limit of this top thing. So yeah, the limit's going to apply here, and that's going to make this thing be e to the negative infinity, which is, hang on, no, it is in fact that I'm applying the limit to this thing down here, yeah. Okay, so limit as x approaches infinity, alpha 1 is going to be preserved, e to the negative 2x is going to be e to the negative infinity, which is again 0, so that vanishes, and this other thing vanishes here. So basically we'll end up with alpha 1 equals 0. And we just repeat this process again twice, and we'll get that alpha 2 and alpha 3 must be 0 as well. So we've just shown that all of these are 0, and that's exactly what we needed to show. So yeah, we got B is linearly independent. Okay, naturally we'll be interested in ways we can minimally represent a vector space. So that is like distill the information in the vector space through the spanning sets. So we call S a basis for V by definition. If span S equals V and S is a linearly independent set. Linear independence gets us this minimality thing. It means that we can't really remove a vector from S to make it smaller. And span S equals V just means we can represent any element of V as a linear combination of elements in S. Yes. And that's the same explanation here. Okay, so the most simple basis is just the standard basis, which you may be familiar with. So for Rn, it's the vectors with 1 in one position and 0 everywhere else, and so on. And for matrices, Ij is the matrix that has 1 in the ijth position and 0 everywhere else. Pretty similar to this. Okay. All bases for a vector space will have the same number of elements. It's just a fact. And as a result, we can define the concept of a dimension of a vector space like so. So suppose V has a finite basis S. then we just define the dimension of V to be the number of elements in S, like so. And this will work for any finite basis S, because again, it has the same number of elements. Not an easy thing to prove, I believe, but it lets us define the dimension of a vector space. Okay, the following three statements are equivalent, supposing dimension of V is n. So, S is a basis of V, S is a linear independent set, and it has n elements. And S is a spanning set, and again has exactly n elements. So spanning set means that its span is V, and it having n elements means it's like the minimum number of elements it can have, so it'll end up being linearly independent. Yeah. Okay, an example of a basis. Consider the degree 2 polynomial vector space. So this is just polynomials of degree 2 with real coefficients. Show that the following set is a basis of this vector space. So these three things. So we kind of want to show that any element in this space can be written as some linear combination of these. And not only that, but that we have this. So it should be clear that the dimension of these polynomials of degree 2 is 3, because they're all polynomials in the form of a alpha plus beta x plus gamma x squared. So we could go with this, the second thing. Actually it'd be more like the third thing. You're showing S as a spanning set, but hang on. Okay, yeah, so we do know that the dimension of this is 3, and so we only want to show that, okay, so we'll go with the linear independence one, which is, suppose that we have lambda 1, lambda 2, and lambda 3, such that this equals 0. Then we just want to show that that will imply that all these lambdas are 0. So after rearranging, we get this second thing. And remember, this needs to be, well, essentially 0 for all values of x. So if we set x to be 0, we'll get that 2 lambda 1 plus lambda 3 has to equal 0. Really, for a polynomial to be 0, all of its coefficients must be 0. So we'll get that this needs to be 0, this needs to be 0, and this needs to be 0 somehow. And so basically, we're just going to have, we have 3 linear equations, 3 variables. We can form a matrix, an augmented one, and solve it. So we reduce it into this. It's got 3 leading columns, so that must mean that the only solutions are lambda 1, lambda 2, and lambda 3 are 0. So so we get linear independence, and we get this. So by our previous lemma, we have that it's a basis. Okay, coordinate vectors. Suppose we have some ordered basis B for V. Okay, then we can represent V as some linear combination like so, with some coefficients. Now if we put each of those coefficients into a vector like this, we get the coordinate vector of V with respect to B. We denote it like this. Okay, so normally to find these, we'd solve this matrix equation where the columns of V are the basis vectors. But it's like, in general, it's not really like that easy. Yeah. Anyway. Okay, so let V be a vector space of 2 by 2 real symmetric matrices. And let A be this. So find the coordinate vector of A with respect to the following basis. So let's kind of convert these matrices into something we're more familiar with. So we'll think about them as actually we'll think of them as R3 vectors, because real asymmetric matrix 2 by 2 is only going to be defined by 3 entries. The third one is guaranteed to be the same as this. But let's have some explanation. Okay. Yep, the basis required is only of size 3. Keep that in mind. And it's best to think about things in terms of the standard basis. Standard basis is easy to work with. And so this is what's clearly going to be the standard basis of symmetric matrices. 1 here, 1 here, and then this one with like 2 ones, because they have to be the same. Okay, so what we're really just looking for is a vector alpha such that this holds. Oh, yeah, such that that holds. So what we can do is we can make the matrices into vectors. I'll show an example of that. So we can make this first one to just 1, -2, 1. Because you can think about it with respect to this basis. You can think of it as coordinate vector with respect to this basis, like as this thing. Because it's a 1 in the first thing, a -2 for this thing, and it's going to be a 1 for here. But yeah, we can just convert them into vectors, form an augmented matrix, and solve it. Note that this is what big A is, and these are our 3 like basis vectors under the standard, as like represented with the standard basis. Okay, we solve using first year methods, and we end up getting this. So that is going to be our coordinate of A with respect to a basis B. Okay, the sum of 2 subspaces is defined like so. Note that hang on, I'll talk about the definition. So it's the subspace formed by taking any element in S, any element in T, and summing them together. So this is always a subspace. Yeah, because if you have some like lambda A plus B, A1 plus B1 plus A2 plus B2, where A's are in S and B's are in T, then you can just go, this equals lambda A1 plus A2 plus lambda B1 plus B2. You know, this is in S, and this other thing is in T, because they're both subspaces anyway. Okay, so if the intersection S intersect T is just this, then we call the sum direct, and we denote it using this notation. Note that S intersect T will also be always a subspace. Okay, dimensions of sum of subspaces. So for finite subspaces, we have the dimension of S plus the dimension of T equals the dimension of S plus T plus the dimension of the intersection. So usually I kind of think about it as this on the other side by subtracting it. So the dimension of S plus T is the sum of the dimensions minus the dimension of their intersection. Okie dokie. Consider these sets. Okay, so one is a set of these matrices, the other is like this stuff, and they're kind of generated in different ways by elements of R. Okay, we already are told that W1 and W2 are both subspaces. Great. Write down a basis for W1. Because W1 is kind of created by this X1 and X2, what we can really do is just separate out the X1 and X2 by like splitting it into two matrices first, one with just X1 and the other with just X2, and then kind of like factoring out the X1 from one of them and the X2 from the other one. I might as well show that. So it'd be X1, 0, 3X1, that would be one of our matrices, and then we kind of just factor out the X1 and take it off, because the X1 we can just think of as like a scalar at that point. And then it would be 1, 0, 1, 3, like here. And same for the X2 vector, sorry, the X2 matrix. Okay, basically in the same way, we do the same thing for W2, and we get this. Okay, for a basis for the intersection, we need something that satisfies these two things for different value, for just values of some x I and some yi. So we just equate these two. And equating them ends up giving us a set of just equations. So these things. So let's see what we can kind of tell from that. Okay, the first one gives us x1 equals y1. Okay, let's look at the next one. Note that doesn't really have x1 and y1, so I'll just avoid that for now. Okay, looking at this, the third one, we can take the x1 off and the y1 off because they're equal to get x2 equals y3. So x2 equals y3, then we can get rid of this from equation 2 and say that y2 must be 0. Then we can take this from equation 4. We have x1 equals y1, so I'll rewrite this equation 4 as 3x1 equals x1 plus x2. Note that the y1 became an x1. Okay, great. So just left with 2x1 equals x2. And note that there are no more additional restrictions on the y1, y2, and y3. So this like sums up the totality of our restrictions. Like there are no further restrictions between x1 and x2. Okay, so yeah, basically x2 must be equal to 2x1. So let's just like substitute that into what a generic thing in W1 must be. We get this. So again, we just factor out the x1 to get this as its basis. Yeah, so this is 1, -2, 3, 1. Okay. So, just a reminder for question 4, we want a basis for W1 plus W2 that already contains our basis for W2. Okay, so we use this fact from earlier to say that to know that the dimension of W1 plus W2 is 2 plus 3 minus 1. Because remember, we calculated these 3 dimensions in the previous 3 steps by finding the bases. So we just get that it's 4. So we only need one more vector to add to our already existing basis for W2. And we know we need to involve vectors from W1 now, so I'm just going to say let's just take any W1 vector that is clearly not in the intersection, and just any of our basis vectors for W1 just suffice. Okay, we're extending our basis for W2, so it depends W1 as well, so just take this vector, which is clearly not in W1 intersects W2. Yeah, because it's clearly not a linear combination of just this one matrix. Okay, that wraps up vector spaces. Next thing is linear transformations. I'll just take a quick 1 to 2 minute break before I start this one though. Okay, moving on to linear transformations. Okay, suppose we have V and W vector spaces over the same field. A function from one to the other is called a linear transformation if it satisfies these two things. This should be pretty clear from first year, from Math 1B. We can combine these two conditions into just this. You can just set lambda equals 1 and you'll get this first thing, and you can set x to be 0 to get the second thing. Okay, show that this is linear. So this is a map from r squared to r cubed. And it works like so on the entries of like some x1, x2 in r squared. So let's just use that thing that we needed to show earlier. So t x1, x2 plus lambda y1, y2 equals, think about what this will equal to. It will be x1 plus lambda y1 plus x2 plus lambda y2. The next thing will be x1 plus lambda y1 minus x2 minus lambda y2. And on the bottom, it's x1 plus lambda y1. And we can sort of just factor out the right things and separate the pluses or minuses into their own vectors to try and extract this out of it, and to try and extract a lambda and then this in terms of yi's as well. So let's just get the one in terms of x's. x1 plus x2, x1 minus x2, and from the bottom, there should be 3 here, and 3 lambda y there, and we can take the 3x1. Okay, and you do a similar thing for the lambda yi's, and then factor the lambda out. So basically just this. Okay, now the kernel and the image. We talked about this for groups. There's very similar notion for linear maps. So the kernel of T is anything that gets mapped to 0, and the image of T is anything in the codomain mapped to something in the domain. And these are subspaces. The kernel and the image are a subspace of V and W, respectively. Okay, the dimensions of the kernel and the image, because again, the subspaces, is called the nullity and rank respectively. And we have this rank nullity theorem that relates the rank and the nullity of a transform. This should be clear from perhaps first year, but yeah. Some of the rank and the nullity is the dimension of the input space. Okay, and these things are important for knowing if transformation is invertible. So, suppose we have a transform from T to W where V and W have the same dimension. And then the following things are equivalent. 1, T is injective. If it's injective, then it ends up being invertible because its output is going to have the same rank as its input, so it's going to output to all of W, and then injectiveness will pretty instantly give you, that's injective and the previous one was surjective, so it means it'll be bijective and hence invertible. So these two things, the nullity of T equals 0 and the rank of T equals n, flow directly from rank nullity as well. And to link invertible with, I can link injective with rank T being n. Yeah, well, if rank T is n, then it's kind of mapping its input space directly into its output. So you expect one output for each input. Okay, so suppose we have some fixed matrix S in a M P by P space. To find a linear map from this space of matrices, like so. So just multiplication by S. Okay, show that rank T equals P squared if and only if S is invertible. So for the first direction, we say, suppose rank T equals P squared. Okay, then the dimension of the image of T is P squared just by definition of rank. But the codomain is also dimension P squared. We should know this. P by P matrices, P squared. So the codomain, so they're equal. So that means the T is surjective. This so they are equal thing is because the dimension of a subspace equaling the dimension of the space itself must mean that they're equal. Okay, so we have surjectivity. Let me get injectivity as well. Oh, well, I mean, you have surjectivity, but then you also have that, what do I have here? Oh, anyway, yeah, so using surjectivity, I can say that there exists a matrix A such that the identity equals T of A, because this is from surjectivity. So the identity is one thing in here, in this space. So I can say there exists something in the input that maps to it. So I can say I equals SA for some A. But that just instantly means that S has an inverse. Okay, on the converse, suppose S is invertible. We can just show the rank T equals P squared. I mean, yeah, that is what we want to show. Note that the dimension of our space is P squared. So we can just show that the image of T equals this. Because then the image of T will have the same dimension, namely P squared. Okay, so we just basically have to show surjectivity. But this should be clear, as for any matrix B, we can map to it like so. Say B equals S, S inverse B, because again, we're assuming S is invertible for this converse direction. And then we convert this part into this, because yeah, S of whatever is just T of that thing. Okay, but then that's surjectivity done. So we prove both ways. Okay, so matrix representation of linear maps. Every finite dimensional linear map, there's a corresponding matrix for it. So suppose T, a map from V to W, is linear, with basis B for the domain and C for the codomain. Then there exists a unique matrix A such that the map under this basis is essentially just the application of this matrix to the coordinate vector of its input for this basis. So a map is just like matrix multiplication with two fixed bases. So if we know the coordinate vector of V with respect to B, we can use it, or we can just use A by doing this to find TV with respect to C. That's just what this thing means. We usually denote A as this, because it relies on the bases B and C. Okay, how do we find A? First we choose ordered bases for the domain and codomain. So like suppose we have these two, we have to start out with these two bases because A depends on them. Okay, suppose B is this. Then, okay, the ith column of A is just going to be the transformation of the ith vector in this basis as a coordinate vector under the basis C. That makes sense. okay, when B and C is the standard basis, like finding this thing is not that hard. But for more complicated bases, it can be harder. Usually when we work with the standard basis, we already have the thing maybe already in terms of that basis. But with other bases, it can be a bit more complicated. But there's a formula we'll get to. But the idea is to convert from the standard basis, is to convert to the standard basis first from your first basis B. Do the transformation with that and then convert back to the potentially more complicated basis C. Okay, so got a map here. S1 standard basis for V, S2 standard basis for W. Then what we get is this formula. Looks kind of weird, but basically you're saying that the transformation from B to C is composition of these three things. So we'll apply you apply things from right. You apply matrix multiplication from right to left. So this first thing ends up just being the columns. Ends up having just columns as B, because you're converting from the basis B to the standard basis. So yeah, the columns of this matrix should be the vectors in B. Hopefully we have this already, or this middle thing, or you can just calculate it just from T of EI under the standard basis for W. So it should have columns looking like this. So you just map the vectors from the standard basis into it. Okay, and this last thing is the inverse of this matrix here, which is the matrix that converts a basis in C to the standard basis in S2. So it's just going to have columns of C, but we do end up inverting it. So that inverse might be a bit more tricky, but still inverting matrices is a pretty standard thing. Okay, consider a linear transformation from R2 to R3 defined as so. We got this basis for R squared and this basis for R cubed. We want to find the matrix of T with respect to these two bases. So again, we use this sort of thing there. S1 and S2 are the standard basis, which we should be familiar with. So to do this, I explained what this was earlier. So that's just going to be the columns of vectors in B, and the other one's going to be pretty similar. So we get these two just by stacking the vectors as columns in our two given bases. Yeah. Middle thing, it'll just be a tiny bit more work. This is just the matrix whose columns are this and that. So we can just apply the map directly to the elements of the standard basis. And yeah, so let's say I'm applying it to 1, 0. What am I going to get? I'll have to scroll up for this. So to apply to 1, 0, it's just going to be 1 plus 0, 1 minus 0, 3 times 1. So 1, 1, 3, which is in fact this thing. And to get the other one, just apply it to 0, 1. Yeah. And then we just kind of have to get the inverse of this one, because remember we need to invert it. Yeah, you can use just however you want to calculate this inverse, but you should be taught in first year. And then yeah, we just combine it with some matrix multiplication. Feel free to do that work on your own, and we'll get this, which is our answer. Okay, suppose T is linear from a space to itself, and we have some subspace. We call X invariant under T if its image under T is a subspace of itself. So yeah, this thing basically. Okay. Got a linear map defined as so. It's just application of the matrix. Okay, define a subspace by this. So this is subspace. It's just the span of these two vectors. Prove that it's invariant under T. So I'll have some more explanation on the following slides, but because of linearity, because we have a basis for these, we can represent any matrix in the form of those vectors. Hang on, as a linear combination of them. Hang on. Okay, so we already know that W is a subspace. We just need to show that this holds. So yeah, we can write any y in T of W like so, and because we have this basis here for W already for free, we can just write this X in W in terms of a linear combination of that basis. So we can write any y in our image of W like this. So that's why we should just need to show that A applied to either basis vector is an element in the span of W itself. Okay, so yeah, I'm just going to call them V1 and V2 for A of the first one and A of the second one. You can just calculate with matrix multiplication, matrix application to a vector to get these two. And then you can use your favorite method to try figure out how it is in fact a combination of our two basis vectors. But yeah, you can see the -4, -1, 1 ends up being this, and then -6, 3, -3 ends up being that, which is in the span of those two vectors, which is in W. Yeah, so y is itself in W, because again, subspace, so applying scalars keeps it in there, and therefore TW is a subspace of W. Okay, two matrices are similar if there exists some other invertible matrix P such that B equals P inverse AP. Note that similarity is an equivalence relation, because, well, I won't go all of it, but I'll just say it works both ways. Because if we apply P and P inverse to the left of both sides, we get P, B, P inverse equals A. So they'll be similar to each other. Okay, A and B are similar if they represent the same transformation but with different bases. Because an invertible matrix in P by P is just columns. Its columns are a basis for F to the P. So yeah, A and B end up representing the same linear transform or different bases. So, okay, there are properties called similarity and variance that hold whenever A and B are similar. This is something that came up in my exam. I was just asked for a bunch of similarity and variance. Okay, here's one. They have the same rank, hence they'll have the same nullity. They'll have the same trace, and oh, what's this last one? Oh, they'll have the same determinants. Okay. But even if you have all these properties, that doesn't necessarily imply that they're similar. For something that is going to be exactly true when A and B are similar, we can look later in this course. Okay, show that these two matrices are not similar. It's going to be quick and easy if we just try to check similarity and variance and find one that doesn't hold. So first we check trace. Oh, okay, they didn't make it too easy on us because the traces are in fact the same. Oh well, let's try for the determinant. Okay, so the determinant of these matrices aren't too bad to calculate. So first one is just 1 times this, minus 0 plus 0 is 4, and for B the determinant is -6. Okay, determinants aren't equal, so that similarity and variant doesn't hold, they can't be similar. And that wraps us up for what? Linear transformations? Yeah, now I'll hand it over to Oscar for what do you got first? Inner products?
Inner products, yeah.
Yeah, enjoy.
Okay.
Just write slow.
Yeah. Alright, so we're going to get started on inner product spaces, and I think a good starting point is to define actually what an inner product is. So suppose we've got some vector space V over a field F, then we say that the inner product is some function that takes two inputs from our vector space V and it maps it to the field that the vector space is defined over. So we would have seen this before, not necessarily like called an inner product, but you might have seen this with the dot product. So the dot product is a type of inner product over Rn, and there's a few like properties that have to hold for inner products. And the first one is that it's sort of this like linearity property. So if you have x plus y, x and then y plus z, and you take the inner product of that, it'll be the inner product of x and y plus the inner product of x and z. And then we get this other nice property that if you multiply one of the vectors by a scalar, you can just throw the scalar at the front of the inner product. Now, the next property is, it's very important, particularly when we look at inner products over complex spaces, and it's that if we switch the order of the inner product, it conjugates our inner product. So for instance, you might have an inner product over a complex vector space, and you might end up with an inner product that's not entirely real. You might have some imaginary component, so when you switch the order of the inner product, it'll just conjugate whatever your answer is. And another really, really important property is that if you take the inner product of something with itself, it's greater than or equal to 0. It's also real, and this is really important. It's equal if and only if the vector that we throw into the inner product is 0. So it's equal to 0 if and only if our vector is the 0 vector. So this will be an important fact that will sort of come in handy a little bit later. But here's some examples of some inner products. So the first one is over real Euclidean vector spaces. It's just you just multiply like the first x component, first y component, add them together. Or so you multiply them together, multiply the second x component, second y component, yada yada, and add all those together. So it's just the standard dot product that we've seen. And we can sort of think of this as a matrix multiplication. So we can do this. We take our x vector and we just take the transpose of it. And then we just do the matrix multiplication with y. And that's really what's going on behind the scenes when we take the dot product. Now, the reason why it's important to think of this as a matrix multiplication is because when we get to complex vector spaces and we look at complex inner products, we have to sort of treat this like a matrix multiplication. But not only do we take the transpose, but we also conjugate it. And we call this the this is the adjoint of x. So the adjoint just means that we transpose it and we conjugate all the terms. So I mean we just think of it like turn x into a row vector and conjugate all the terms and yeah, we end up with the complex dot product. There's also another form of this. So this is, we can even generalize the complex dot product even further, and I'll show you what that looks like. So it looks like this. And these are, of course, vectors. I'll draw vectors over them. So this is the complex inner product in its most general form. And what we say is that, like, it looks almost the same, but we've got this matrix like sandwiched in the middle here. And this is a Hermitian matrix. So what a Hermitian matrix just means is that if you conjugate it, conjugate all the terms and transpose it, it's the same matrix. So this form we won't use as much, although this was actually a question in the online Mobius test. So it's important to know this. And another fact is that this Hermitian matrix is positive definite. So the determinant of it is always going to be greater than or equal to 0. So yeah, I mean, this has a lot of applications in stuff like beyond this course. Like if you look at quantum mechanics and stuff like observables and like position, momentum, spin of specific quantum states, you use this form of the dot product. So obviously we're not going to touch on that in this course. This is a course on linear algebra, but interesting fact to know. And then we can also define inner products for function spaces. So if you want to take the inner product of two functions, assuming that they're like continuous functions defined on the interval AB, you can just integrate it from A to B. And then it's just the integral of f of x, g of x for all f and g, an element of C, A, B. So yeah, it sort of shows that inner products are, it's kind of arbitrary, like you can define them however you want. I guess that's like the real beauty of it. It's like very, very generalized in the sense that like you can define any operation in like any arbitrary way. So we have different types of inner products for different spaces that tell us different things. So now we can use inner products to, yeah, sounds good. Yeah, so we can use inner products to define something called orthogonality. So we've probably heard this term before, probably a little bit familiar. So we say that two vectors, x and y, if they're in some vector space V, they're orthogonal if their inner product is 0. So I mean, we've seen this before. If you take like the dot product of two vectors and you show that it's equal to 0, I mean, you can conclude they're at 90 degrees, they're perpendicular to each other, or they're orthogonal. So we're just kind of generalizing that idea. We say that they're perpendicular, or sorry, not perpendicular, orthogonal, if their inner product is 0. And I mean, we just write it like this, x perpendicular to y. So it's quite, the notation is, it's quite nice, it's very intuitive. So now we can go one step further and we can look at orthonormality. So we can say that vectors, suppose you have a set of vectors that are here. We've got some set of vectors vi, from I going from 1 through to n. We'll say that this set is orthonormal if you pick any arbitrary I and j, you pick any two random vectors out of this set of vectors, if you take the inner product, it should equal the Kronecker delta. Now, if you're not familiar with what that is, the Kronecker delta is basically if I and j are the same thing, it's equal to 1. So, I guess to like put that into terms that make sense, if you take some vector in this orthonormal set and you take the inner product with itself, which will just give you the magnitude, it's analogous to taking the dot product of a vector with itself, you get 1. So effectively you're saying that the norm of the vector, or the magnitude of it, is just 1. And then if you take the inner product of any two vectors that are different, so I is not equal to j, then it's just 0 because they're orthogonal. So yeah, orthonormal vectors will be important when we start to look at things like QR factorization. So yeah, just a few terms that we want to define, just to, you know, yeah, just some interesting things to note. Now we can redefine, and I say redefine because we've already met vector projections before, whether that's first year uni or in high school, like Extension 1 Maths. But now we can generalize, since we've got this generalization for the dot product, we can define it now using inner products. So we say that if you have, again, x, y, are vectors in V, then the projection of x onto y is the inner product of y and x divided by the inner product of y with itself times the vector y. Now, this here we can just think of, if they're like vectors that are over Rn, we can just think of this as y dot x, and we can just think of this as the magnitude of y squared, or the squared norm of y. So, yeah, now it's really, 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 really important that if we look at this inner product at the top here, it is so important that you have these vectors in the right order, because conjugate symmetry is a thing. So if you have, I mean, this doesn't really matter if they're real valued vectors, but oftentimes we're going to deal with complex inner products, or we might get asked to project some complex vector onto another complex vector, and because of that conjugate symmetry, it matters what order you put it in. So in general, whatever vector that you're projecting, the vector that you're projecting onto something, so the input here, the x, must go on the right side of this inner product here. So, because otherwise you're going to get, it's not going to be correct. It's not always, you can't always switch them around. You can only do that if they're real valued, but if they're complex valued, then, it gets a bit yucky. So, it's nice, we can then get this nice property here, which is that the x minus the projection of x onto y is perpendicular to y. And I guess I'll just draw a little diagram here just to illustrate this. So if this is x and this is y, then this one here is the projection of x to y. So therefore this is just going to be x minus the projection of x onto y, which, I mean, we can just see is perpendicular to y, or it's orthogonal. The writing is sort of falling off the end of the screen. It's a bit messy, but you get the idea. And this is a really important property, because we're going to, this will come in handy when we look at this thing called the Gram-Schmidt process. So we started with a fact. We say that every finite dimensional inner product space has got an orthonormal basis. So given any basis, doesn't have to be orthonormal, doesn't have to be orthogonal, doesn't matter what it is, we can always find an orthonormal one. And you might be thinking, well, how do we do that? Like, given any arbitrary basis, you can just, how do we just extract an orthonormal one out? Well, it's this thing called the Gram-Schmidt process. And as painful as this thing is to compute, it is very, very, very helpful. So the idea is that we start with an orthogonal basis. Note that this is orthogonal. It's not, so V, the basis of V's is not orthogonal. It can be any arbitrary basis, doesn't matter what it is. So then we say, okay, let's suppose that there exists an orthogonal basis. So we're not going to jump straight to orthonormal, we're going to jump to orthogonal, because in order to find an orthonormal basis, we have to find the orthogonal one first, and then divide through by all the magnitudes. So we'll say, okay, let's suppose there exists this orthogonal basis, W's, or all these like W vectors, right? And I'll underline that. It's like, well, how do we construct this? Okay, well, it doesn't matter what the first vector you pick is. You can pick any arbitrary vector at first. So we're going to say, well, let the first vector of our non-orthogonal basis be the first vector in our orthogonal basis. So in other words, we're going to pick V1 to be our first element, and then we want to start constructing vectors that are all orthogonal to V1. So V1 is sort of going to generate this orthogonal basis. So we say, okay, well, let this equal this. Now, we can use the property we can use this really nice property here, that x minus the projection of x onto y is perpendicular to y, or it's orthogonal to y. I'm going to stop saying perpendicular. It's orthogonal to y. We can use that fact to generate an orthogonal vector. So we'll say, okay, well then, if v2 minus the projection of v2 onto w1 is orthogonal to w1, let's just let the next member in our orthogonal set be equal to that. And that's exactly what we do here. Say that. Now we can continue this process by doing all these vector projections, and I mean W3, we say okay, well, we're going to find something that is orthogonal to W1 and W2. So then we end up going with, we choose this as our vector for W3. We say it's equal to this. And as a sanity check, to make sure this is orthogonal, we'll just say, like, take the inner product of W3 and W2, and this is equal to the inner product of, and we'll just sub in what this W3 is, just to make sure that this is in fact doing what we want it to do. That's W2, and this is, so yeah, we'll notice that this projection of V3 onto W1 is going to be some, or this term here, this thing here, is some scalar multiple of W1. So I'm just going to write that as lambda W1. And then we're taking the inner product with W2. Just like that. Now, we know that, I mean, we can expand this out using the fact that we can just expand out inner products from our properties that we looked at earlier. To be this with W2 minus, and I'm going to do the lambda W1 and the W2. So I'm going to throw the negative lambda out the front because we're allowed to do that. W1, W2. Okay. By definition, W1 and W2 are orthogonal. I mean, we've shown that. We know that these two are orthogonal. So that means that this inner product is just 0 here. And this inner product on the left is just the property that we had up here, which is this. They are orthogonal to each other, so that means the inner product is 0. So this is going to be 0 minus 0. So what we've shown is that W3 and W2 from this, the inner product is 0, therefore they're orthogonal. So we know that this process that we're doing here, we can trust it. It will give us something that is, it will give us what we're looking for. Okay, so we're going to actually put this into practice, and we're going to actually do an example to get a feel for what this is like. So let's suppose that we have vectors v1, v2, and they're elements of C3. So we have v1, we define it as that vector, 1, I, 0. v2 is I2, 6. And we want to find an orthonormal basis for the span of these two vectors, which is orthonormal to with respect to the standard inner product on C3. Now we want to be very cautious. This here, C3, we have complex valued vectors. So we have to be very careful with our inner products. We're going to make sure we get it the right way around. So we just use the Gram-Schmidt process, and we say, okay, we'll let suppose that we've got some orthogonal basis consisting of W's, and we have a non-orthogonal basis consisting of our two vectors v1, v2. So that's going to be the span of v1, v2. We'll say, okay, let W1 equal v1. Okay, sweet. That's simple enough. Nothing crazy just yet. And then now we use the fact that v2 minus the projection of v2 onto W1 is orthogonal to W1. And we'll let that vector be W2. So now we have this complex inner product here. Right? And I'll just compute this real quick. So this will be 1, I, 0, I, 2, 6, which, recall, is just 1, negative I, 0, and I think I'm going to run out of space, maybe not. Ah, sweet. Yeah, so it's just this, right? And what we've done is we've transposed the first vector and we've conjugated it. We've looked at we've taken the adjoint. We've done the conjugate transpose, which is what we defined our complex inner product to be. And then this just gives us 1 times I, be I, minus 2I, plus 0. Why did I write 6? That is supposed to be, let me rub that out. 2I, yeah, minus 0. So this is just negative I. And that's where this comes from. And I'll leave you to check that the norm of the first vector is just 2. But we end up with this. And this here is our perpendicular, or our orthogonal vector, W2. Now they ask for an orthonormal basis. So, yeah, we've constructed an orthogonal basis, but that's obviously not good enough. We want an orthonormal one. So we just find the magnitudes of each vector, respectively, and we just divide through by it. So I hope that you trust that the magnitude of this vector is 1 on root 2, and that the magnitude of this vector is 1 on 3 root 2. It's a bit, the 1 on 3 root 2 one it's a bit tricky to show that, but it's just it's a lot of algebra, which, I mean, it's stuff that, it's not conceptually hard, it's just a bit of algebra bashing. So I'll leave you to verify that if you are unsure, if you don't believe me. So yeah, here is our orthonormal basis. And yeah, just like that, we can use that's the beauty of Graham-Schmidt. We can produce really nice orthonormal bases like that. Okay, so the next thing is that we want to generalize projections onto, we can generalize projections further, and we can look at projections onto subspaces, not necessarily just vectors. And we begin by defining something called the orthogonal complement. Okay, so the orthogonal complement is of some vector space, vector subspace W, is a space of all vectors X which are orthogonal to every vector in W. So we can sort of write that the orthogonal complement is, I guess, X element of. So say that W is a subspace of V, which we've got here. So if we pick any X in V, then if the inner product of X and W equals 0 for all W element of W. So we sort of say that it's orthogonal to everything in W, which, I mean, it kind of makes sense. That's why we call it the orthogonal complement. The naming convention is quite nice. But we have some theorem that follows from this. So if we have any finite dimension vector space V, and suppose we take some subspace W of V, then the direct sum, the sum of, it is a direct sum. So W plus the orthogonal complement gives you the entire space. And that, intuitively, we can think about this by saying, well, suppose W is some subspace of V, then it spans certain dimensions of V. Say it doesn't span every dimension in V, but it spans a few, right? But not all of them. Then, if we want something to be orthogonal, it has to span a different direction or a different dimension. It can't be spanning in the same dimension, because then it won't be orthogonal. So what you're saying is that every single vector spans a different dimension to W, because they're all orthogonal. And what you end up getting is those missing dimensions in W, as in the dimensions of V that W doesn't span, gets covered by the orthogonal complement. So everything that W doesn't span, every dimension that W doesn't span, W perpendicular, or the orthogonal complement, does span that. So not only is the sum direct, but it covers all of V. And if you don't believe me that the sum's direct, let's just suppose we have some W. Suppose it's not direct, which means that the intersection is non-zero. So we'll say let W be in the intersection of W and W perpendicular, where W is non-trivial. It's not just a zero vector. Okay. So that means that W is an element of big W, not sponsored, and that W is an element of the orthogonal complement. Okay, so if it's in both W and the orthogonal complement of W, trivially we can just, it's not really trivial, but we can just take the inner product of W with itself, and by definition it should be 0. But W is not the 0 vector. So yeah, so that's a bit unfortunate for us. because this is impossible. This is a contradiction because the inner product has to be positive definite, which means that not only is it greater than or equal to 0, but it's only 0 when we plug the 0 vector in. But we said that W is not the 0 vector. So that means that the intersection of this must be the 0 vector. There's nothing in there. So the sum's direct. Sweet. And what this means is that if we take any vector x in some finite dimension vector space V, then you can express it as some... You can express it like you can decompose the vector into some component in belonging to W, the subspace W, and some component belonging to the subspace W, the orthogonal complement of W. So, yeah, now we can look at orthogonal projections. Now we can sort of begin to formalize this. So if X can be expressed as the sum of A and B, where A is something in W and B is something in the orthogonal complement, then the projection, then A is what you get when you project X onto W, and B is what you get when you project X onto W complement. And that makes sense because you're just taking the component of X in W, and you're taking the component of X in the orthogonal complement. And that's what we're sort of saying A and B is. So you can decompose it like that, which is really nice. So, yeah, this implies a very useful fact that since, I mean, this was the property we were looking at before. If you have X minus the projection of X onto W, it'll be perpendicular to any vector in W. So the inner product would be 0. Hence, it has to belong to the orthogonal complement. So this is sort of building on from that property that we use when we're looking at Gram-Schmidt. So yeah, it's very nice. Now, let's take a look at this. Let's actually project onto a subspace. Enough of me talking about all this theoretical stuff. We'll have a look at an actual example. So suppose that we've got some subspace, W, which is spanned by the vectors V1, V2. Now, I want to find what happens when we project X, which is just the standard basis vector, the first standard basis vector in R4, onto W. And the inner product that we're using is just the usual dot product. Okay. So how are we going to do that? Well, let's suppose that we just say, okay, let Y be the projection of X onto W. This is what we want to find, right? Then that means that we can decompose Y into some vector along V1 and some vector along V2. And it also satisfies this fact. And that's from the property on the last slide, this thing here, yeah. It follows directly from this, because we said that the projection of X onto W was Y, so that means that X minus Y belongs to the orthogonal complement. Yeah, so since we've got, we have a basis for W, right? And that is, that's just given by V1 and V2. Those are our basis vectors because that spans the space. So we just want to make sure that X minus Y is orthogonal to both V1 and V2 because that belongs to the orthogonal complement. So I'll save you a lot of the horrific algebra. So we just take dot products and we say that they're 0 because it belongs to the orthogonal complement, and the dot product is the inner product that we've defined over this space. So when you substitute in, this is just subbing in Y, because we said Y was lambda V1 plus mu V2. So X minus Y is just going to be X minus lambda V1 minus mu V2. And we take the dot product with V1, so that's equal to 0, because orthogonal complements, and we end up solving this through, you end up getting this condition here. And then we repeat the same thing for V2. So we end up with this condition here. Okay, 2 equations, 2 unknowns, simultaneous equations. I don't really need to go over that. That's quite straightforward. So we end up with this. We get that lambda is just 2 on 11 and mu is 3 on 11. So then we say that the projection of X onto W, which we said this was our Y vector, is, since it was like it was lambda V1 plus mu V2, we just sub in the things that we found. And we add it all together to get our final projection. Now, if you're not a fan of all that working, I've got good news for you, because there is a simpler way to do this. Granted, you sort of have to memorize this, which is unlucky. I guess you got to pick your poison. So we have a thing called a projection matrix. So if W is a subspace of V, and then we let A be the matrix consisting of the basis vectors of W. So the column space of A is going to be the basis for W, right? So what I mean by that is like, if this is our basis, V1, V2, then A is just going to be the matrix with this as the first column and this as the second column. So it'll look like a 4x2 matrix with these two vectors thrown in there. Okay, so we'll get back to the definition. Yeah, so then the projection of some arbitrary vector B onto the subspace W is given by this. So it's A times the inverse of A star A times A star times B. So A star, again, I'll clarify what this is. This is we take A, we conjugate it, and we transpose it. So this is like the adjoint matrix. We transpose the matrix, conjugate all the terms, which only matters if it's a complex matrix. Otherwise, we're just really transposing it, and conjugating does nothing because they're all real numbers. So if we just work out if we work out what this is, then we can instantly, just get the projection. This is a bunch of matrix multiplication. And the real beauty of this is that A star A, I guess it has to be invertible since, A is going to be an invertible matrix since it consists of the basis. So this formula works, and this is what it looks like. You just define the matrix A, so it's those two vectors in our two basis vectors. Then we just do A star A, it's that. Then we calculate the determinant and take the adjunct matrix, meaning we just swap the diagonals, swap the terms on the diagonal and multiply the terms on the off diagonal or the opposite diagonal by -1. And then we throw the whole thing together like this. Big matrix multiplication. I'm not going to go through this. This is quite simple stuff. And we arrive at the exact same result. So this is more of just a mechanical method. You don't really have to think doing this, which is often quite nice. I guess you can save your brain power for the other questions on the exam. So then we move on to this thing called QR factorization, right? So we'll start with the theorem of what QR factorization is. So suppose that we've got a full rank P by Q matrix. That just means it's linearly independent columns. So there's no redundant columns. It means we can factorize our matrix A into matrix Q times matrix R, where Q is a P by Q orthogonal matrix and R is an invertible Q by Q upper triangular matrix. That just means that everything below the diagonal is 0. Okay. So it looks a bit like this. This is the form that we're going to get it in. Okay. And I think this should actually say, I think this should be orthonormal. I'll just double check that. Nevertheless, we will proceed. So yeah, again, orthogonal, right? Orthonormal. Gram-Schmidt. Alarm bell should be going off Gram-Schmidt. We're going to be using that. So yeah, so Q is these vectors here. Q are the normalized vectors of. It's like we find an orthogonal basis consisting of our WKs by Gram-Schmidt, and then we normalize these. We just divide through by their respective magnitudes to get an orthonormal. So it'll be orthonormal. So I guess it is an orthogonal matrix. So we'll just jump into it. So let's look at an example. Okay, so we've got this matrix B. We want to do the QR factorization. Okay. Immediately by inspection, full rank matrix, these columns are not linear, they're not scalar multiples of each other. So we are good to proceed. So we want to use the Gram-Schmidt algorithm. So we extract the first vector, this one here. Extract this vector out, call it A1. And by Graham-Schmidt, we'll just say that this is the first vector in our orthogonal basis. Boom, this right here. And then we say, well, using the fact that A2 minus the projection of A2 onto W1 has to be orthogonal to W1, let W2 equal that. And A2 is just what we get when we extract the second vector out of this. Okay. Now this is nice because these are all real numbers, so it's just a standard dot product. So the dot product will give us this, divided by the magnitude of W1, so it'll just be the magnitude of this thing. Magnitude squared, I should say. Yeah, or the squared norm, whatever term you want to use. So yeah, it'll give us 4 over 4, and then we subtract the vectors, and we get this. Okay, so we have our orthogonal basis right here. Now we normalize these vectors. Okay, so we divide through by their respective magnitudes. So this first one has, this here has a W1 equals square root 4, which is 2. And then we just find, the magnitude of this next one, which I think is root 10. And we just divide through by that to get our orthonormal vectors. Okay, so Q1, Q2, we've already found our Q matrix. That's all there is to it. That is the Q matrix. So those will be the 2 columns. Now, we have to calculate inner products. So just looking back at the QR factorization thing, we said it was upper triangular. So everything below this diagonal is 0. We don't have to worry about it. Now, this... so then we've got the magnitude of W1, which we found. That was, that was what we just calculated before, like when we're normalizing our vectors. Now, since we're only going to get these terms, right? This is going to be our matrix. This is what we're looking at, because we only had 2 vectors. So we have to calculate this inner product here. And we're going to do exactly that. Q1, A2. So scrolling all the way down, Q1, A2, it's just a simple dot product. I don't really need to go over that. You just take the dot product of Q1, which is this vector here, and A2, which is the second vector in our B matrix, and we end up with 2. So we combine all this together in this form, and we get this this nice matrix factorization, QR factorization. So we use this because it sometimes helps us with stuff like least squares, all those kinds of things. So it's, I guess, for the sake of our convenience, and also because they ask you to do this in the course. So so we're going to look at adjoints. Adjoints is it's a special kind of linear map. So suppose you take any linear map that goes from V to W. There's a unique linear map, and we call this the adjoint, T star, right? And what it says is that if you take the inner product of W with T of V, so what V gets mapped to in W, then it's the same as the inner product of this weird adjoint map, mapping whatever the adjoint maps W back to V, the inner product of that with V. So if this property holds, if you can find a linear map, given some linear map T, if you can find some linear map T star that satisfies this, that linear map is called the adjoint of T. So for a matrix, we can, suppose we have a matrix, we can just transpose and conjugate all the terms. That's an adjoint. So that thing that we're looking at, like A star, that's an adjoint of A. But oftentimes we get maps that are a little bit funky, where the 2 spaces might have different inner products, and that's where it gets a bit. You have to use quite a bit more thinking to try and work those problems out. But we'll look at some properties of adjoints. S plus T, if you take the adjoint of S plus T, it's just the adjoint of S plus the adjoint of T. Very nice. We take the adjoint of alpha times T, where alpha is any scalar. Then it's alpha conjugate times T star. So we have to conjugate the alpha. That's really important. Put an arrow there. Yeah. Then if you take the adjoint of an adjoint, it sort of undoes it, and you just end up back with the original map, T. And if you've got some linear map U which goes from W to V, then the composition, the adjoint of the composition is just you've switched the order around and it's the adjoints. So this is a bit similar to how, like, if you have matrix A, B, inverse, think of it like this. Think of it a bit similar to this. Like, you just switch the order around and you throw the adjoints or the stars on there in the same way that you switch the two matrices around and you throw the inverses on there. So I'll put quotations around this because it's a way that you can think about it. It's a little bit similar. So yeah, adjoint matrix maps, these are the nice ones, these are the fun ones. If you have a linear map from V to W, then the adjoint map of T is just the conjugate transpose of T. So you might have to do a question that requires you to, like, quickly calculate an adjoint of a matrix, and you just conjugate it, transpose it, and you're done. So unfortunately, we're not going to look at an example that easy. We're going to pick something a little bit trickier. So this is from last year's final exam, and it's got a lot going on here. So we say let X be the vector space R2, okay, with the standard inner product. Okay, that's nice. We're just working with the dot product. And then let Y be the vector space, the polynomial space of polynomials of degree at most 1 with real coefficients. So we have this strange inner product that we are defining over our vector space Y. And that is the inner product of these two polynomials is P of 1 times Q of 1 plus P dash 1 times Q dash 1, where the dash just denotes the standard derivative. It's nothing crazy going on. So we define some linear transformation T, and it's given by this. So this is T that takes some vector from R2 and it maps it to a polynomial in P1. Now, that is a typo there. Let me get rid of that. We're going to find the inner product of P0 plus P1T with T of X, and hence we're going to find a formula for the adjoint map. So the reason why we're working out this inner product was because we can use the definition of the adjoint map. Okay, so this question is quite daunting. There's a lot here. So we want to come in with a strategy. Okay, so this is our game plan. This is our strategy. So we're trying to find an adjoint map that satisfies the definition of the adjoint. Now notice that this is the inner product over P1, and this is just the standard dot product over R2. So in other words, if we can calculate what this thing here is, and if we can get it in the form of the dot product, like we just do a little bit of manipulating, rearranging stuff and get it in the form of the dot product, that'll give us precisely what this is. So yeah, we're going to evaluate P0 plus P1T and T of X in a product of that, and then use the fact that the little adjoint thing in our right-hand side is just the standard dot product on Rn. So we want to keep this in mind, and let's just say that Y is T star of P0 plus P1 of T. So now we're going to evaluate the left-hand inner product. So we're going to use the definition of what that inner product is, and that is just this here. So we're going to use this, sub in some things, and yeah, we get a big mess of algebra, but I assure you this is nothing too deep. It's nothing crazy. We just expand a little bit, and the idea is that we want to try and take this and get it in the form of the dot product, that being x1 y1 plus x2 y2. That's just the dot product of x dot, that is also x dot y. So if we can get that, then happy days. Okay, so we just do all this expanding and simplifying, and eventually we get to this point. We can simplify to this. So the idea is that we want to extract an x1 out and an x2 out and express it as x1 times something, x2 times something. And in particular, this we just think of as y1. This we just think of as y2. Okay, so that is just the components of our vector. So what it's saying is that if you take the adjoint and you throw p0 plus p1 of t, the corresponding vector that you get is 3p0 plus 5p1, which is just y1. And the y component is 2p0 plus p1. And that's because we know that this inner product is just the standard dot product. So we end up with this formula. And we're done. Yeah, that's all we have to do. So, yeah, it's very nice. So we're going to look at some types of maps. So there's a few ones that are interesting. So if we have some linear transformation from V to V, and it's a linear map, then if T star, the conjugate transpose, or its adjoint, is the inverse map, then it's unitary. And I'll tell you a really cool fact about this. If T star equals T inverse, then T times T star equals, it's a T times T inverse, which is just the identity matrix. So we can show that if T is unitary, then T times its conjugate transpose, or T times its adjoint map, is just the identity matrix. So, yeah, that's a special type of map. Hermitian maps are maps that, when you take the adjoint, it's self-adjoint. So it means that T is equal to its own adjoint. So when you transpose it and conjugate it, you get the same thing that you started with. Again, Hermitian maps are very important. Yeah, very important in quantum mechanics if you're interested in that at all. A lot of observables. So sort of going back to that generalized complex dot product. Yeah, stuff like momentum, spin, position, Hamiltonians, all that kind of stuff are all Hermitian operators, or they're all Hermitian like matrices, which is really cool, self-adjoint. But yeah, this is just kind of a property, it's self-adjoint. And then we have a thing called an isometry, which sounds a bit scary, but it just means that if you take some vector and you apply a linear transformation to it, the norm is preserved. The length of it doesn't change. So the vector doesn't get scaled, doesn't get longer or shorter, none of that business going on. So an example of like an isometry is a rotation. Rotation will preserve the length of the vector. Or if you have a reflection, that preserves the length. So rotations and reflections are isometries. So there's an important fact here. Yeah, so here the adjoints are based on the standard inner product. So yeah, if we have a matrix T, then the adjoint matrix is just the conjugate transpose. Now, fun fact about isometries is that a map is an isometry if and only if it is unitary. Alright, so let's have a look at this. We have a map from C2 to C2 and it's defined by this. Is it isometric or is it Hermitian? Okay, so we'll say that T times WZ equals 2Z, and this is negative W. Alright, so by inspection, we're going to say that T, we can pull a matrix out of this. We can say it's going to be, just imagine a 2 by 2 matrix in your head. And the top left component times W gives us 0. That 2Z is going to be like top left component times W times the top right component times Z, just by matrix multiplication. So we know that we have no W's in the top component because it's just a 2Z, so this is 0. And we have 2 Z's, so this is going to be a 2 here. Similarly, this will be negative 1, because we've got a negative W, and we have no Z, so this is going to be 0 here. Okay, is it isometric? We know that a matrix must be an isometry if and only if it's unitary. Okay, we know that unitary matrices, if you multiply T by T adjoint, you get the identity matrix. So let's do exactly that. T times T adjoint This will be 0, -1, 2, 0 times. Now, I don't have to conjugate anything because it's all real. This will be 0, -1, 2, 0, which will give us 4 here, and then this will be 0 here, then we get 0 here, and we get 1 here. So this is very clearly not equal to the identity matrix. So it's not an isometry. Is it Hermitian? These two matrices here and here are not equal. So T does not equal T star, not Hermitian. Yeah, not Hermitian. Yeah, and then yeah, this is sort of just the written. Is it written out? Yeah, not isometric, not Hermitian, as it's not equal to its adjoint. Now, the method of least squares. This is an important thing. This comes up very often. They ask a lot of questions on this. So yeah, we're just effectively trying to find a line of best fit or some kind of equation of best fit given a few points. So yeah, so the method of least squares, I'm sure you're quite familiar with what this is. Just, I guess, the concept of it. So if you have like some system AX equals B, then the solution to the normal equations, which is the equations that govern what this, I guess, like function of best fit or line of best fit, whatever you want to call it. Yeah, these are the governing equations. A star A times X is A star B. Now, for Math2501, we don't have to worry about, I mean, we're only going to be dealing with like real matrices. So, I mean, A star is, the conjugation it does nothing. So, we just have to worry about transposing it. Yeah, it's a little bit yuckier when it's got complex valued stuff. But I mean, it's nothing too bad. So, yeah, these are like the equations that we want to solve. So, I much prefer, because this one, again, takes basically all the thinking out of it. So if A has independent columns, so the columns are linearly independent, then we know that A star A is invertible. And therefore, the general solution to the normal equations is given by this. And it's important that it's invertible because if it's not invertible, then this inverse doesn't exist. So this is very, very similar to the formula for projection matrices. So if you want to try to remember the projection matrix formula, just throw an A onto the front of this and you're done. So if you remember one, I guess it's kind of easy to remember the other. So yeah, if we just plug our matrix A and our vector B in, it'll just spit the solution out. It's really nice. So here's one from the 2021 final exam. Suppose we have a matrix M and a vector Y. We want to find the least squares best fit solution to mx equals y. Okay, we want to use this formula. This formula is very beautiful. We want to use this. So we calculate m star m. We take the inverse, so divide through by the determinant, switch the diagonals, and multiply the off diagonals or the other terms by -1. Now we put this all together by multiplying this by m star and then multiplying by y. So with a bit of matrix multiplication, we get this. So you get this answer, and then you can simplify it to this. So our least squares solution is just this. Yeah, like it's as simple as that. If you know the formula, it'll come out very, very quickly. So that yeah, that's all there is to inner product spaces. So I'm going to try and see if I can. Okay, yeah. So we're going to move on to determinants, and I'll try and make this quick just because we're running a little bit over time. So we're going to jump straight into it, and we're going to look at permutation. So this isn't like super, super, super important, but I mean, it's a bit of interesting theory. So a permutation is just a reordering of a set of n items. So we can think of this as like each item in our set is sent to another item. And we can denote, so suppose we take a set omega, 1 to yada 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 n. We can say some permutation on this set sigma is p1, p2, yada yada yada, pn. And we say that 1 is sent to p1 and 2 is sent to p2. So we're sort of just mapping all of these items in our set to p1, p2, yada yada to get our permutation. So it's nothing too crazy. And the fun thing about this is it forms a group under it forms a group called the permutation group under composition. So for instance, S3 would be the group of permutations on the set 1, 2, 3. And another important fact is that we represent the kth element of a permutation as sigma of k. So that'll be important when we look at what the definition of a determinant is. So we'll throw another bit of terminology. If we permute two elements, means we swap them around, we call it an inversion. Now, we are fully equipped to define what the sign of a permutation is. So if we have some permutation sigma, which is in the permutation group, so it's one of the possible permutations that you can make out of a set of n elements, we denote the sign, genius naming convention here, sign of sigma, it's quite obvious. It's an indicator of how many inversions we make in the permutation sigma. So if there's an even number of inversions, the sign is 1, and we call it an even permutation. Otherwise, if we have an odd number of permutations, like 1, 3, 5, inversions, then we say that the sign is -1, and we call sigma an odd permutation. So, again, quite nice. Yeah, I mean, it's I think it's quite quite logical. Now we're going to just look at a simple example. We want to find the sign of this permutation sigma here, and we want to identify what sigma of 2 is. Okay, so if our set omega is 1, 2, 3, if we have this set here, to get to our permutation sigma, we just take these two elements and we just kind of switch them around, and you see we end up with this. So we've done one inversion. So that's one odd number, so we have an odd number of inversions, so the sign is -1. And now sigma of 2 is the second element in our permutation, which is going to be this, 3. Sigma of 2 equals 3. So we don't need to know the permutation group theory. We don't need to know this stuff like in great depth. But hopefully, I guess we can sit here and kind of appreciate it for what it is. So properties of the sign. If you take the sign of the composition of two permutations, sigma and tau, it's the sign of sigma times the sign of tau. So this is a group homomorphism. So it's the permutation group defined under composition, and this here is it's just a homomorphism. So I think it's kind of cool. So the next property is the sign of a transposition is -1. So you do one transposition, it's the sign of that is just -1 because 1 is odd, so it's an odd permutation. Now, so again, transposition just swaps two elements. Now we can say that every permutation can be expressed as a composition of transpositions. That's what this whole idea of it being a group under composition is about. So the sign of a permutation is -1 to the k, where k is just the number of transpositions. Because you can think of it as if I have 5 swaps, 5 transpositions, that's just one transposition composed with the next transposition, composed with the next transposition, composed with the next transposition, etc. And we end up with this, -1 to the k. Okay. Now, here is an interesting formula, or not formula, interesting definition of the determinant of a P by P matrix. So we can define this using permutation groups, and S of sigma is just the sign of sigma, and we're kind of iterating through every possible permutation on the permutation group of P elements. So this formula, or this definition, it's kind of cool, but we're almost never going to use this. As for computing determinants, this isn't the route you want to go down. I mean, by all means, you can go for that, and I commend you if that's your preferred way of calculating determinants. But we have a much better way, and it's the theorem just below. And it's this idea of ijth minor matrices. So what that means is that, or I guess I'll just say the theorem first. So the theorem is that the determinant of the matrix can be expressed as, for any fixed j, as the determinant of A times, the determinant of A is given by the sum from I equals 1 to P of -1 to the I plus j times Aij times the determinant of Aij, determinant of the matrix Ij minor matrix of A. So the ijth minor just means that if we have a matrix like something like this, if you have a row or a column that has only one non-zero term in it, so look at this first column. We've got this. This term here is the only non-zero term in this. It's the only non-zero term in this column. So what we can do is we can, and I'll switch to a different color. We can create what's called the ijth minor. So we wipe out this column and this row, like that. And therefore the ijth minor is just the matrix with the ith row and jth column removed. So the ith column and the jth row removed. So this I guess it's just going to be, I feel like it should be row and column, but it's whatever. So the ijth minor in this case is just going to be the matrix with 2, 8, 9, 2. So we kind of annihilate that column and that row. And we just take what's left over and throw it into a smaller matrix. So to be, instead of like a P by P matrix, it's now a P minus 1 by P minus 1 matrix. And this is so useful for calculating determinants, especially big determinants. So the determinant, here's some important properties. These are fantastic properties. The determinant of an upper triangular or lower triangular matrix is simply the product of the diagonal terms. That's pretty riveting stuff. It's very nice. Additionally, the determinant of a matrix is the same as the determinant of the transpose. So the determinant of a matrix is invariant under transposition. Now, the determinant of A is equal to the conjugate of the determinant of the adjoint matrix. So we can think of this like A star is a conjugate transpose. So I mean, if we really conjugate this, you get AT. I'm not very good with this. Yeah, there's this AT, and then it sort of follows from this fact here that the determinant of the A star conjugate is just the determinant of A transpose, which is the determinant of A. So that's how we get that third property. Very nice. Okay, we've got a bunch more. So number 4, if a permutation is applied to the rows of A, if you switch two rows around in your matrix, the determinant is multiplied by the sign of the permutation. So if you swap row 1 and row 2, the determinant becomes -1 times what the original determinant was. Now say you swap row 1 and 2, determinant is multiplied by a negative. Now say you swap row 2 and 3, you multiply the determinant again by a negative, so you get the same determinant, right? So it switches from positive to negative every time you switch a row. So number 5, if any row of A has a multiple of another row added to it, the determinant is unchanged. So basically, if you do your row operations, like row 1 is row 1 plus, I guess I should say that you, row 1 plus like 3 row 2. Stuff like that, when we do our Gaussian elimination, does not change the determinant, which is lovely. We can simplify matrices into a nicer form and then apply, we just apply the Gaussian elimination to simplify it, and then it'll hopefully be in a form that's a bit easier to compute. So number 6, if a row of A is multiplied by a constant alpha, the determinant is also multiplied by alpha. Very important. That'll come up in the next example that we look at. But yeah, like if you have a matrix, if A is an element of like n by n matrices over the reals, then the determinant of alpha A equals alpha to the n times the determinant of A. And that's because you have n rows and you multiply alpha in all of those rows. So you have alpha times alpha times alpha times alpha for every row. And if you have n of them, you have alpha to the n times the determinant of A. So again, this was another question in the online Mobius. So useful fact, it's quite neat. So we also have that any matrix with a 0 row or a 0 column has a 0 determinant. Also another property that we could probably throw in there is that if you have a matrix with linearly independent columns, then it's also going to have a determinant of 0. And that just sort of arises from the fact that if the columns are linearly dependent, so they're not linearly independent, then it's going to have a non-trivial kernel. The matrix will have a non-trivial kernel, which means that the linear transformation given by that matrix is non-injective. If it's not injective, it's not bijective, it's not invertible, and if it's not invertible, the determinant is 0. So that's just a brief little SparkNotes summary of the proof. You can have fun trying to prove that to prove that yourself. It's really neat property. So we're going to look at. We're finally going to have a look at, bringing all this together and looking at a matrices question. So this is really like, in a lot of the past papers, they don't ask many questions on matrices beyond the true-false ones. But this is like one that's quite a bit involved. So if A, B, C are real numbers, and A is some 3 by 3 real matrix given by that, explain why the determinant of A is A plus B plus C times the determinant of B. Okay. So while it might not immediately be obvious, we can apply some row operations to A. Namely, we can get A into this form. And I'm not going to go through all of the algebra, but if we say that row 2 is row 1 plus row 1, is just row 1 plus row 2. So you add row 2 to row 1, and then we also add, after that, add row 3 to it. So you can just say add the second and third rows to 1, and we end up with a matrix that looks like it'll be A plus B plus C. So we'll get a matrix that's a little bit like that when you add the second and third rows to the top row. And this is just the matrix B, but we're multiplying the top row by A plus B plus C. So, since we multiply a row by some scalar, in this case A plus B plus C can be a scalar because they're all real numbers, we just multiply the determinant by it. So, this is just a bit of working. Nothing too fancy. Yeah, we arrive at this. And yeah, this is just, we can pull the a plus b plus c out when we take the determinant, and we just say it's the determinant of b. So hopefully that makes a bit of sense. Now, the next part, we're not done just yet. We want to explain why the determinant of b is equal to this. Okay. So we want to look at the B matrix, and we want to think of some kinds of operations we can do to maybe get it into the form that they're asking for here. So what we're going to do is we're going to leverage the fact that determinants are unchanged under transposition. So an implication of that is that we can subtract columns from each other, because you're effectively just transposing it, subtracting rows and stuff like that. So you transpose it, doesn't change the determinant. You add multiples of different rows, doesn't change the determinant. Then you transpose back, doesn't change the determinant. So instead of going through that big roundabout way, we're just going to subtract columns. So what we're going to do is we're going to say C2 is C for column. C2 is just going to be C2 minus C1, and then C3 is just going to be C3 minus C1. So if we take column 2 and subtract column 1 off it, then we take column 3 and subtract column 1 off it, we end up getting this matrix. And so yeah, this here is, and I'll annotate this, is C2 is C2 minus C1, and then this here is C3 is C3 minus C1, and we end up with this determinant. We have it in the form that they want it in. So I feel like that's good enough reasoning as to why that's equal to that. Now, hence, find the determinant of B and give it in the factored form of determinant. Oh, and hence find a factored form of determinant of A. Okay. I mean, we look at B, and the glaringly obvious thing that is, staring right at us is that this is 0, this is 0, this is 0. So everything above the diagonal is 0. We have a lower triangular matrix, and we know from property 1, from all these, I'll scroll back up. Jeez, this goes quite far. Yeah, by property 1, the determinant of an upper or lower triangular matrix is simply the product of the diagonals. Okay, this is very good news for us. This is, fantastic. So all we do is we just multiply the diagonals. That's all there is to it. So yeah, the determinant of B is just going to be A minus B minus C times A minus B minus C. So that's just like negative A plus B plus C times negative A plus B plus C. The negatives cancel, and we just get A plus B plus C squared. Now we want a factored form for the determinant of A. Well, how convenient. In part 1, we deduced that the determinant of A is just A plus B plus C times the determinant of B, which is this property here, is this one here. And we've just worked out that the determinant of B is A plus B plus C all squared. So yeah, we end up with the determinant of A is just A plus B plus C all cubed. Yeah, and that's how you solve that problem. So there's quite a bit there. Few neat tricks in there, and obviously knowing the properties of determinants is very helpful. But yeah, so we arrive at that, and that wraps up. So that wraps up all of the stuff on determinants. So really, it's not a lot in determinants. It's more so just knowing the properties. We don't have to worry too much about the permutation group stuff, but it's interesting nonetheless. So yeah, that concludes the first half of Math2501 and 2601, the seminars. So the second seminar will be taking place later today. So feel free to tune into that. We're looking at eigenvectors, Jordan canonical forms, and matrix exponentials and ODEs. So yeah, good luck with your studies, and yeah, hope all goes well.